This video I'm going to be working some practice problems for the modeling test for AP Precalculus. And these are just some questions from the progress check on AP Classroom. But I think we got some good ones on this one. The table gives the cost per ton for a certain type of landscaping stone for orders between 0 and 10 tons. An order of 5 tons of stone would cost $40 each for the first and second tons, $39 each for the third and fourth tons, and then $36 for the fifth ton. C models the cost for an order of X tons of stone, which is the best function type. Okay, this one is going to be piecewise linear, because really, like, what they're saying is that the slope is, or the total cost, which would be like $40 times the number of tons. Okay, so maybe that's a slope of 40. And then we have a slope of 39, which is very close. Okay, I had to draw it quite a bit less, but that's all right. Then 36x, so it bends down a little bit. Then 31, which is a lower slope, and then 24 after that. And so that's, a bunch of lines pieced together. That's what piecewise linear. All right, because it's the total cost. All right, anyway, a model rocket is launched from a site on level ground. This looks like it's going to require a calculator. Let me get that out. It's telling us 1 second after the rocket's launched, it has a height of 20.1. Okay, 1 additional second later, well, they would say that, but quadratic regression using 0, 1, and 2. Okay, so we're going to need 3 data points, run a regression, predict the rocket will land back on the ground. Okay, so T 0, 1, and 2, and we will need 3 data points in order to run a quadratic regression. Height, okay, launched from a site on level ground, so h of 0 equals 0. After 1 second, it's 20.1, and then 1 additional second later, it's 30.4. So we're going to need to put that data into the lists. Stat, edit the lists, 0, 1, 2, then 0, 20.1, and 30.4. And then we're going to stat calculate. Let's see, it asks for a quadratic regression. We're going to need to reason with the graph of the regression equation, so I'm going to definitely store that into y1. And then, okay, there we go. Okay, this is not free response. I don't need to report my findings here. I'm going to go to y equals. I doubt I have the stat plot turned on. I'm going to turn on plot 1. I'm going to zoom to the stats, because that will also, oh man, I thought that would. Okay, it's okay. It'll be all right. I am going to need to zoom way out, though, on an x level. Oh, yeah, x is going from 0 to 2, but we change that to 0 to 10 and see what happens. It's up, and then it's coming down, all right, and we found the time at which it hit the ground. That's going to be the 0 of the parabola, and so that's a left bound. This is a right bound. That would be a good guess. 5.102, and that's answer choice D. Right, now we've got residual plot discussion here, and let's see, make sure I get that all on the screen. So we've got linear, quadratic, and cubic. Based on the residual plots, which is going to be true? All right, I'm just going to say right now, linear and quadratic are bad models, and cubic's a good model, because I see no clear pattern on cubic, but I do see clear patterns on linear and quadratic. So, the cubic model should be used, yeah. Okay, I mean, like I've said before, you can read a pattern into almost anything, but that scatter on the right for the cubic residual, that is kind of like what we're saying is the look of no pattern. All right, then year versus population. Right. Based on, okay, and so we'll need to do an exponential regression, so I'm just saying that right here. A times b to the x is calculated for the 5 data points. All right, so we're going to go to stat, edit the list. Okay, x equals 4 represents 2004, so we're going to start at 4, 8, 12, 16, and 20. And 22.4, 24.3, 26, 27.9, and 29.2. All right. And we're going to get out of there, go to the calculate menu, run an exponential regression. Let's see, yeah, we're gonna predict when the population reaches 35 million. I've got a, no, I don't, no, yeah, okay, I think I probably lost my work. No, no, there we go. Call for y1, calculate, all right, there we go. Okay, so now we've got a regression equation in there, and we could graph this equation, graph y equals 35 and see where they intersect. That's an option we've got, but we also have the option to go look at the table, and that's what I'm going to do right now. I'm going to use the table. So I'm going to first go into the table settings, and I'm going to say the table, I want this to start at 25 because that's the lowest answer choice that I see. And then we're going to jump up by 1 each time I asked for the table. So table, there we go. And so we want the first year where it went 35. Okay, there it is. That must be, okay, so it went from 30 or like 34.9 to 35.5 between 30 and 31. So that must mean 2030. Okay. Now, exponential function E and linear function L both pass through the points 0, 2, and 1, 6. All right, I noticed this one when I was putting together this problem set. I found this one particularly interesting. I think what we're going to want to do is run two different regressions on this data set. And I think at this point I'm going to clear the RAM and go over here, edit my lists, do 0, 2, wait, no, okay, that's not how I expected that to go. We're going to edit the lists. 0 and 1 are my input values that correspond to 2 and 6 as output values. I'm going to, we could pretty easily figure out what, just a second, figure out what, the linear equation is or the exponential equation. We could do it algebraically, but this clearly allows the use of a calculator, so I might as well do it. Did I actually store that? Okay, I did. So now I'm going to go back, stat, calculate an exponential regression, except I'm going to store that one into y2. I'm going to calculate. And that's going to be 2 times 3 to the x. But what's most important is that I've got this one and that one kind of like put in y1 and y2. And if f of x equals L minus e, the linear minus the exponential, wait, no, that's, okay. Oh, goodness. Please stop. Okay, there we go. Don't love this program, this emulator, but it's better than what I had on my computer previously, which was nothing. All right, so y1 minus y2, I've got it in there. We're interested in the maximum value of f. It must be mostly negative, and I'm going to just, well, I'm going to go over here and turn off the graphing of the first two, because I don't really need to see those. What I really need to see is the difference. And I'm just going to hope it's visible. Sure enough, there it is. Okay, so what we're going to do is we're going to calculate the location of the maximum. That is to the left of the maximum. That's to the right of the maximum. Give it a guess. 0.545, and the output that corresponds to that is 0.540. Okay. That's the because there was value of f, so that's the y coordinate at the maximum. All right, now we've got a table giving 5 ordered pairs, which is true about the nature of data. Okay, I'm looking at the answer choices. So basically, all right. So, all right, an exponential regression does not necessarily, like, the y values do not have a common ratio of 1.094, because if I multiplied 10 by 1.094, it would not be 10.75. I know that. I think it would be 10.94. And so that one's out. Then common ratio that y values can be found as 1.075. Well, I'm going to test that by doing 11.688. No. 11.688 divided by 10.75. And I'd get 1.087, which is not 1.075 or 1.25 or 1.094. So I'm not liking that one either. Now, if we subtract 7 from each y value, I'm interested in that option. So if I subtract 7 from each y value, I'd have 375. Okay, subtract 7, that would be 4,688. Subtract 7 would be 586. Subtract 7 would be 7,325. And what I'm going to do is I'm going to start with multiplying 3 by 1.25. I'm going to get 3.75. And I'm going to multiply the answer by 1.25 again. And then I'm going to keep doing that. 4,688, 586. I really wish that was 859. I'm not loving that. But then 7.325. Okay, I think. Oh, I know that C is the right answer. Okay, I see it now. This is not exactly true on its face. Like that's just not true, right? Because if you subtract a constant or add a constant, you can reveal an exponential type relationship, because it's still exponential if it's got a vertical translation. So, yeah, that one was a little weird. I think that might be why it was on the progress check and not on your AP exam this year. All right, number 7 is the first table giving coordinate pairs that are part of a larger data set. Using the 5 data points, we did 3 different regressions. Okay, that's nice. It is known that using linear, quadratic, and exponential fit these 5 data points well. Like how they quantified that, said well, it's good. So which of the following additional pieces of information could help select a single best model? In AP Precal, that's going to be a residual plot. That is, I don't see anything about a residual plot. Okay, so I'm going to actually have to look at this. All right, so 2, 3, 4, 5.5, and 7. So I'm seeing some increase. Okay, this would not help. Here it is. All right, as x increases, y increases without bound. Well, I think you've got an exponential curve that does that. You've got a quadratic with a positive leading coefficient. I forgot if I do that, it'll actually look nice. And then if you had a linear function with a positive coefficient, positive slope, we would see only it was increasing arbitrarily as x values increased. And knowing that the minimum y value in the data set is less than 1. I don't know about that. I don't see what that's getting at, so I might come back to that later. Knowing that when x values are negative, the corresponding y values are always between 0 and 1. I do like the sound of that. Yes. Okay, and knowing that the y-intercept is about 0.5, no, I think we could have any of these 3 having, y-intercept of any type. That doesn't sound like it would pin it down to 1. All right, the minimum y value in the data set is less than 1. I guess what we're saying is that, okay, because I see it. Because it's discrete data, it's really just like, a collection of these along maybe an exponential curve. And if the minimum y value in the data set was less than 1, that could be possible if I was approaching the x-axis like it looks like I am there. Or if the y-coordinate of the vertex on the parabola was below 1, they could be either exponential or quadratic. But if we knew that for all x less than 0, y was stuck between 2 values, that would mean we had a horizontal asymptote. Wait, I was crossing out that one. This is basically implying that we've got a horizontal asymptote, I guess, or it's sinusoidal. But they didn't offer that as an option. So it looks like there's going to be a horizontal asymptote. The only one of these that has a horizontal asymptote is exponential, so that's how we could choose a single model. I kind of liked that one. That was interesting. What do we think about it? So here we've got, okay, function y equals f is a linear. Okay, I'm going to need to write that. And then g is an exponential model. Because of the limited number of data points for the residual plots, it's difficult to determine if there's a pattern. As a result, both models f and g are being considered. Okay, so we looked at the residual plot and it didn't tell us anything. That happens. K represents the sum of the absolute values of the residuals of the linear model f. That's different. P represents the sum of the absolute values of the residuals in model G. Okay, so I'm just going to say this to remind myself that K goes with the linear model and P goes with the exponential model. If the selection of an appropriate model is based on the residuals, which of the following is true? All right. Now, knowing that the absolute value of the residual is the error, I feel like that means we would want to minimize the total amount of residual. So no way they're going to actually have us compute this, right? Okay, let me look and see. Maybe 3 of these are like logically impossible. Okay, if k was k was greater than p, then exponential model would be preferred. Okay, so, if k was bigger than p, yeah, linear is out. Because there's more residual. There's more error in the approximations. But if k is less than p, then the linear model I feel like would be better. So that takes this one out. Okay, I've got a different idea. I'm going to try to do this faster than making a residual plot. So I'm going to go to the catalog and I'm going to make sure diagnostic is turned on. And this is not part of AP Precal, but I'm hopeful that this will work. Okay, evidently what they want us to do for this one is type in all of this data, which I don't like. But it doesn't matter what we like and what we don't like, right? It's what we're called to do. And so 20, 30, 40, 70, and 100. We're going to stack calculate a linear regression. I am going to store it into y1 in case I need to make a residual plot. I heard that it's possible to make one on this, and I just kind of forgot how. Okay, now we're in business. I'm seeing an r squared value that's not like 0.999. So r squared is 0.935. And that is, r squared does have to do somehow with some of the residuals. I forget how. I have known at one point in my life, but I definitely don't know right now. I go over there. I'm going to do an exponential regression. I'm going to store that one into y2 just in case, because if the r squared values are close, then I'm going to say, if this was your AP exam, okay, 0.992. I like that better. That's materially better. It's not like it was 0.941 or 0.927 or something like that. If that was the case, I would want to go in and make the residuals and actually add them all up. But man, that's not happening. I know it's possible to do on the calculator. I'll show you what would happen if I was going to do that. What I would do is I would edit the lists and I would let L3 be the predicted value from the linear model. And then list 4 be the residual because I would do actual minus predicted L2 minus L3. Then L5, I would make that the exponential model. And I would then make list 6 the residual for the exponential model. That's crazy. That can't be what you're supposed to do. But also, I know that r squared is not what you're supposed to do either because that's not part of our course. I don't know. I know that the exponentials model is better, so I would think that p would be the lesser one, and I'm going to go with it based on that level. But I promise that there are no questions on my unit test in my AP Precalculus class that require you to make a judgment based on the value of r squared. That's just not something we're going to be doing. All right, students in a stat class examined individual student test scores for a large group. Each test score is paired with the reported time the student spent studying. Well, I mean, that's troublesome because I know that data is not reliable. The class observed that when study time doubled, test scores generally increased by 5 points. For example, a student who studied 2 n minutes generally scored 5 points higher than a student who studied n minutes. This is going to be a logarithmic situation. I mean, this is like textbook, input, output. If the output values form an arithmetic sequence, so like, p and then p plus 5 and then p plus 10, and then also, when the amount of study time doubled, that's a geometric sequence or an exponential pattern in the input and a linear pattern in the output. That's logarithmic. All right, so for non-zero constants a and b, which is going to be best, log, there you go. I actually think that one, I think I saw that word in AP Classroom, and therefore thought that was going to be this was going to be the unit to drop it in. But I actually think this would have been better when we were first studying logs. This was a really good example of a situation in which the input values are have a common ratio, and then the output values form a linear pattern. That's the language that I could use. All right, so here, this is kind of related to the semi-log plot thing. I've just found this one interesting. I don't know, maybe it was supposed to be a logarithmic discussion or whatever, but in AP Precalculus, it's all part of Unit 2, right? The semi-log plot and all of the exponential and logarithmic stuff, it's all lumped together. It's just in my class, I saved all of the modeling stuff to the end because me and my pre-cal teammates, we were kind of unsure about what this is going to look like, and just kind of kept putting it off and saved it for last. So this one, A is halfway between 100 and 1,000 on a logarithmic scale. The logarithm base 10 of the value is 50% greater than the logarithm base 10 of 10 squared. Yes, that's it. I know that one's right. Wait, I feel like C also looks right. The value is definitely not the average of 0 and 1,000. That's 500, we know that, and I don't think that's the case. The value is the average of 100 and 1,000. Oh man, I'm gonna have to think about this one. I've thought about this one for longer than I would care to admit, and I think I was approaching this from a place of process of elimination, and I'm going to be approaching this in a more forward direction. Now, I know for a fact now, after having thought about it for a while, I can certainly eliminate answer choice D, because the logarithm base 10 of 10 to the 2 is the exponent I put on 10 to get 10 to the 2. Right? And that's going to be a 2 exponent. Okay, so 50% greater than 2 is 3, and 10 to the 3 is 1,000. So I know that A is not sitting at 1,000 because it would be on top of 1,000 if that was the case. Okay, now, the average of 10 to the 2 and 10 to the 3, I mean, 550, who am I to say, right? I don't know about that, or whether it's 500. But if I look more closely at this, and just think about this scale, in terms of what the exponent of 10 is, it would make sense that this spot right here, that's halfway in between 10 to the 2 and 10 to the 3, where each jump measures a jump of the exponent by 1, that's going to be a jump in the exponent by a half. So that's going to be 10 to the 2.5 power. Right. Then, that's why I am believing that it is answer choice C. The logarithm base 10 of the value is 2.5, because I know that log base 10 of 10 to the 2.5 equals 2.5. Maybe, I mean, I think that this is one we're supposed to, like, really know our business on. Because I found A and B, honestly, I didn't see anything wrong with them. But I think it's also partially my lack of experience with semi-log plots. But I expect if you're watching this video, you also have a lack of experience with semi-log plots and you're trying to get some more. And that's why we're here. So, all right, next one. Which of the following is the graph of an exponential function where the horizontal axis is standard and the vertical axis is logarithmic scale? I really hope y'all get a question like this. Oh, wait, if they say exponential function on a semi-log plot, it had better look linear, okay? And there's only one of these, so there it is, okay? At least on this one, we had all semi-log plots. I've seen multiple choice questions that not even all of the graphs are on a semi-log plot. But, we're looking for that linear pattern because we know that when we graph an exponential function on a semi-log plot where the vertical axis has been logarithmically scaled, that's going to produce a graph that looks like a line. All right. And number 12, a regression is calculated on a data set of coordinate pairs x, y. Resulting regression model is a plus b natural log x. The same model, this is just a log property question. What is the value of c in terms of b? Okay, so the same model, so f of x and g of x are the same. That's what they're saying. This is just going to be some algebra. But again, I saw that regression model word in AP Classroom and I just snipped the question. So f of x equals g of x. A plus b natural log x equals a plus c log base 5 of x. Oh, that shouldn't be too bad. I'm going to subtract a from both sides. And I'm going to do that with my eraser. And then I'm going to say, all right, I'm going to say, what is the value of c in terms of b? Oh, so I need to solve for c. All right, we're going for getting this thing on its own. So I'm going to say over here, c equals, I'm going to have b times natural log x, which I'm going to just call log base e of x, divided by log base 5 of x. Now this is a good question here. What I need to remind you, I don't immediately see, it's going to either be, oh no, we're going to apply multiple log properties, aren't we? Yeah, I think we are. Okay, the first one is a particularly obscure one that I have not had reason to talk to you about recently, and that's the change of base formula. All right, so what I'm going to say is, well, I'm just going to write it how I usually write it. Log base b of a is equal to I'm missing something here, but anyway, I'm just going to keep going. Basically, natural log a divided by natural log b, or any base. So, if I wanted to convert, what am I missing? I'm definitely missing something here. Okay, I see a potential way forward. I have not worked it out yet, but I'm kind of tired of having to stop and think about these. What I'm going to do is I'm going to do this on that log base 5 of x. So I'm going to say log base 5 of x must equal natural log x divided by natural log 5. I don't know if this is what you're supposed to do, but it's what I'm going to do. I'm going to say, all right, that denominator is going to become a natural log x divided by natural log 5. So now I've got c equaling b multiplied by, okay, natural log of x is that numerator. And I'm going to actually put that over 1. And because I'm going to be dividing by log base 5 of x, which is now a fraction, I'm going to flip and multiply. So that would be natural log 5 divided by natural log x. And then I will cancel off the natural log x's, and I will get b times the natural log of 5, which is here. I was thinking maybe they were going to, because you could also say that that would be the natural log of 5 to the b. But evidently they weren't feeling that aggressive with the log properties. Okay, that one was quite a ride. Okay, let's keep going. Still got more problems. Certain nuclear chain reaction, number of atoms increases. I'm not a chemist, but that sounds really suspicious. How is, maybe they're just bringing in new atoms into this reaction. At times 700 milliseconds, they're about 1500. Okay, so 700, 1500. And then at 770, there's 3000. Okay. Using a logarithmic regression, a model T is constructed. Okay, yes. So what we need to do is go in and edit the lists. And so 700 and 770. And I'm going to delete 1500, 3000. All right. And then I'm going to calculate a log regression. That's option 9. I'm definitely going to need this to go into, I'm trying to click y1, and then we're going to calculate. All right, great. R squared equals 1. Well, yeah, there's only 2 data points. So we want to know when the number of atoms reaches 10,000. Let's see. We're looking between 800 and 1200. So I'm going to do this one by graphing. I already did one with a table. So I've got this one. I need to get rid of... Come on. There we go. It's taking on average 3 clicks for it to take. I've got this one. I'm interested in where it reaches 10,000. I'm definitely going to have to manipulate the window, though. I'm going to say, all right, x, well, 880 up to, the biggest thing I see is 1200, maybe 1300. And maybe the scale should be 100, because I don't want it to be like super crowded with tick marks. Then y. Oh, I just need to have 10,000 in it, so 9,000 to 11,000. I don't know, scaled 500, who cares? And I should be seeing 2 graphs. I've got the log curve there, and I've got the y equals 10,000. We are going to calculate the intersection between blue and red. We're going to give it a guess, even though there's only one intersection. I'm going to go nice and close. And we get 1,201, which was answer choice D. Now here we've got a semi-log plot of the graph of f, and it's on a semi-log plot where the vertical axis is logarithmically scaled. We are seeing a line. It must be exponential. Oh. What are the values of a and b? Oh, okay. So this is exactly the type of situation I had tried to avoid. I am going to have to take this, like, again, I really hope that this would not happen on the AP exam, because all the rest of the examples we've seen before this, they would have said basically 1, 10, 100, 1,000. Okay, and I am taking this to mean that the labels on the y-axis, let me see. Maybe I'm supposed to know that if they say the y-axis has a logarithmic base 10 scale, that the actual height of the function f is going to be 10 to the 3 at x equals 0. So that's what I'm saying. When I plug in x equals 0, I need to get f of x equals 1,000, or yeah, 10 to the 3 is 1,000. So, they can't be saying. No. Okay. I'm going to do this, totally on faith, and I really don't like this problem. But I'm going to say take the base 10 log of both sides. Log of f is going to equal log of a plus log of b times x. We've done this process enough times, and if you aren't familiar with this, you need to go back and watch the semi-log lesson and do the semi-log homework, because we did this quite a bit. And do the semi-log quiz while you're at it. Yeah, so it's like log f is the y scale, is mx plus b. And it looks to me like the slope, if you could even, like, I really tried to not call it that and tried to not do rise over run on this grid, but it went up by 3 when it went to the right by 10. So I think log of b, log base 10 of b, which maybe I will write that in there, is equal to 3/10. It's like the slope of that line. And then we would take 10 to both sides power, and we're going to get b equals 10 to the 3 over 10. Okay, so yeah, I see that. I don't love it. I can work with it though. And then log a is going to be the intercept, so log base 10 of a equals 3, and that means that a is 10 to the 3, 1,000. Okay, and you couldn't even see that answer choice, but hopefully you were looking at the problem set on your own. Man, I just think that question could come with something else, or maybe have not been there. Next one's talking about an exponential function graphed on a semi-log plot. Y-axis is a logarithmic base 10 scale, like we just saw. All right, the graph of f is a line on the semi-log plot. The graph of function g is also a line on the same semi-log plot. Slope of the graph of f is the same as the slope of the graph of g. Okay, this is another hard one. So what we're going to need to do is figure out the y-intercept on the graph of f, or also think about what g looks like on the semi-log plot. So I'm going to take the log base 10 of f, and that's going to equal 0.8x plus 2.4, right? If I take the base 10 log of 10 to a power, it's just going to be that power. And so that means that log of g, if they've got the same slope on the semi-log plot, 0.8x, and the y-intercept is half of the y-intercept of f. Okay, this is not as hard as I thought it was going to be. Then if I undid this, g of x, I'm going to take 10 to both sides power, equals 10 to the 0.8x plus 1.2. And then I'm going to plug in g of 2 equaling 10 to the 1.6 plus 1.2, because 0.8 times 2 is going to be 1.6. All right, I need to get out to the main menu. All right, now I'm in business. So 10 to the, is this going to work? Yeah. 2.8, and they get 630.957. That's going to be 631. Right, that one was actually pretty interesting. I like that one. All right, and then 16, I think this is the last one. Nope, there's just still more. All right, so again, semi-log plot, the graph looks like a line. It must be exponential. Yes, there we're seeing it. Why does the graph appear linear? No. Log base 10 of f can be written as a linear expression of x with a constant rate of change of... No, f of log base 10x is not something we do in this class. I mean, unless we're just doing like composition of functions. Oh, I didn't even see that. A horizontal axis does not have a logarithmic scale at all. So it's going to be this one. Yeah. Okay. Now, the last one. I neglected to include the table. Okay, well, I'm going to go get the table for you. Hopefully by the time you're watching this, that your version of the PDF has the table on it. Okay, there's the table. So, and I also just watched a quick instructional video on how to run a sine regression. Obviously, we know where the command is in there, but I did one today in class where it kicked me an error. And I thought it was because I didn't, kind of make a guess on the period, but I just kind of, maybe it has to do with the number of data points. It also is going to talk about the number of iterations, and the video I watched did not go into what that meant. So negative 3.2. Okay, I'm going to just do 0 minus 3.5. Have that negative button on my computer. I don't think I I have the patience to click all those numbers in. All right, there we go. So we've got them all in there, and I'm going to calculate a sinusoidal regression. 3 iterations, it's the standard, works for me. I'm going to leave that blank and see what happens. I'm going to call for the y1 to store this because it's going to want the value of f of 6 predicted. And, well, I can take out negative 5.2. That's definitely going to be wrong because it looks like that was negative 4.8 looked like the minimum. But who knows? Maybe I'm thinking of something else. I already did it by grabbing it up there. If you're working with an 83 or an 84 that doesn't have that y equals command, you go variables, y variables, function mode, y1. All right, and let's just see what happens. Okay, it was happy. Yeah, it told me I had a non-singular matrix last time, and I know what that means in a matrix algebra, linear algebra situation, but I don't know what that has to do with sign regression, but I also don't know how sign regression really works. So I've got that. I stored it into y1, right? So I should be able to just compute the value of f of 6 and press enter and get negative 3.92. Yeah, there we go. All right, feeling good about that. That's surprising, but that's the sinusoidal function model that used all the data. It's okay. That's what it told me. I'm gonna go with that. I don't have any others, right? Yeah. The only thing that I didn't hit, I feel like on this one, was a quartic regression. I did those. I did some of those in class, but a lot of my people were taking state standardized testing for U.S. history today in class. So if you were not in class, you need to be aware of quartic regression. And I think I'm just going to leave that at that, and that's going to be all for this video. Thanks for watching.